everyone, welcome back. Today we'll be solving Leetcode's Jump Game 3 using DFS and BFS in Golang. As usual, we'll cover visualizing the algorithm and live coding solution. In case you're new to my channel, I'm a software engineer, I've worked in Silicon Valley, and specialize in Go. Now let's get started. Given an array of non-negative integers, we are initially positioned at the start index. We have the option of either jumping forward to I plus the array value at the index, or backward with the same. We want to find out if we can reach any index with the value 0. Let's take a look at this example. First, we start at index 2, and we can either jump forward 2 steps or backward 2 steps, which should give us either index 4 or 0. At index 4, we can jump either forward 2 or backward 2 again, which would give us either 6 or 2. Now 6 is out of bounds because n is equal to 5 in this case, and 2 we have already visited it before, so we no longer need to check this node any further. At index 0, we have the option of either jumping forward 3 or backward 3. Jumping forward will give us index 3 and backward negative 3, which is of course out of bounds, so we just check the index at 3, which is actually 1, so we can either jump forward 1 or backward 1. And that would give us either index 4 or index 2, both of which we have actually visited before, so we no longer need to check any further. So with that, we have successfully went through the entire array, and we do not actually reach this index with value 0, so we return false. We can see that really this is a graph traversal problem, where given the start index, we want to look through the graph and determine if we can reach a node which corresponds to an array index that has the value of 0. We should also know that for graph traversal problems, there are 2 common ways to solve it, DFS and BFS. In this video, we'll cover both the stack and recursion ways of using DFS as well. First, let's explore using DFS stack to solve the question. We take a look at this example. We start from index 5 of the array, and we have an empty visited array and stack. Now, since we have not visited index 5 before, we add that to the visited array, and at that index, there is the option of either jumping forward or backward 1, which gives 6 and 4. Since they are both not visited and are valid array indices, we append them to the stack. Now, when the stack is not empty, we pop the last element, which is index 4, and add it to the visited array. At that index, there's the option of jumping forward 3 or backward 3, which will give us 7 and 1 respectively. Since 7 is out of bounds, we do not need to check that any further, and since we have not visited index 1 before, and it is a valid index, we append that to the stack. Since the stack follows a last in first out order, we pop 1 and add it to the visited array. At that index, there's the option of jumping forward 2 or backward 2, which would give us 3 and negative 1. Of course, the negative index is out of bounds, so we do not need to check that. And since we have not visited 3 before and it is valid, we append that to the stack. Again, we pop it and add it to the visited array. Now at index 3, we check and see that it has the value of 0 in the original array, which means that we are successful in finding an index which has the value 0, so we return true. That's it. Now let's code it out. First, we initialize the visited map, which will track whether we have visited the index in the array before. And we use a map in this case because we need to easily check the element with all one-time complexity. Then we need to implement the stack using slices. If you're interested to find out how stacks and queue work in Go, subscribe for my next video. Now we start checking from the start index, so we set that to true in the visited map, and the current index to start. And we do some sanity checks to make sure that the current index, to see if it's already 0. And if that is the case, then we just return true. Now we check the adjacent nodes. There is the option of either jumping forward, so we need to add its value to the current index, or jumping backward, so we do subtraction. Now if they are both valid indexes, we append them to the stack. While the stack is not empty, we need to continue checking. So first, we pop the last element of the stack, which would be length of stack -1, and we update the stack. We set the current index to true in the visitor map because we're starting to check it. And again, we see if the value is 0. If it is, then we have successfully found the element, so we return true. And otherwise, we need to check the forward and backward index to see and update the stack. So if we have not visited the adjacent nodes, and of course, if it is valid, then we append it to the stack. Similarly, we need to do the same for the backward index. Check more than equals to 0 since we are jumping backwards. Append it to the stack. And then we just go through the loop. So finally, we go through everything. We still cannot find any index with the value 0. That means that we have not been successful, so we return false. There we go. Next, let's explore using DFS recursion to solve the question. We'll use the same example as before, except this time around we start from index 0. Again, let's build the tree. So from index 0, we can either jump forward or backward. And since the negative index is out of bounds, we don't check it any further. And from index 4, we can either jump forward 3 or backward 3. So that would give us 7 or 1. Since 7 is out of bounds, we only check index 1, which means we either jump forward 2 again or negative 2, which would give index 3 or negative 1. Since the negative index is out of bounds, we only check index 3, and we realize that at index 3, the value is 0, which means we are successful, and hence we return true. Now, from the graph, let's formulate our recursion thought process. We see that at each step, there are two possibilities that we can make. Either A, we jump forward, or B, we jump backwards. So this will be the recursive calls we need to make at each step. And when should we terminate the recursion? When either the array is out of bounds, as we see here, or if we actually manage to find an index whose value is 0. So with that in mind, let's code out the solution. First, we create the visited map just like before, and call the recursive function, passing in the starting array, the visited map, and the start index. Now, let's implement the recursive function. So as mentioned before, our terminating conditions would be if the current index goes out of bounds, or of course if we have already visited the index before, so we don't need to actually check it again, so return false in that case, or if we actually manage to find the index with value 0, so in this case return true. Finally, we need to mark the index as visited, so we do not visit it again, and recursively make the calls with the array, visitor map, and the index plus the value at the index, which is either we jump forward, or, as mentioned before, we can jump backward. So in that case, we need to subtract the value. There we go. Now this DFS takes time complexity O(n) and space complexity O(n) to run. Lastly, let's use BFS to solve the question. We'll reuse the same example and tree we have built at the start of the video. Initially, we have an empty visited array and queue, and we put the start index into the visited array and add it to the queue. Now since the queue is not empty, we pop the first element, so the current index we're checking is 2, and it has adjacent nodes 4 and 0, both of which are valid and unvisited, so we append them to the queue. Now queue follows a first in first out order, so we pop the first element 4, add it to the visited array, and check its adjacent nodes, which is 6 and 2. Since 6 is out of bounds, we do not need to append it to the queue, and 2 we have already visited it before, so we do not add it as well. Next, we pop the first element of the queue again, which is 0, add it to the visited array, and check its adjacent nodes, which is 3 and -3. -3 is out of bounds, so we only add 3 to the queue, and while it's not empty, we pop the first element again, add it to the visited array, and from 3 we can either jump to 4 or 2. However, 4 we have already visited, so we do not need to check it. 2 is also visited, so we don't need to check it. With that, we have come to the end of the algorithm, and we have not been able to jump to any index with value 0, so we return false. Now, let's code it out. As with before, we want to initialize the visited map, and we implement the queue with a slice. If you want to find out more about how stacks and queue work in Go, subscribe for my next video. Now we append the start to queue and set it to visited. Also set the current index to start. Now as long as the queue is not empty, we want to continue checking. So first we pop the current index from the head of the queue and update the queue. Now we check if the current index has the value 0, then return true because we have successfully found it. Then update the index to visited and calculate the forward and backward index. Now if the index is valid and we have not visited it before, then we want to append it to the queue. Similarly, we want to do the same thing for the backward index. If it is more than equals to 0 and unvisited, we want to append it to the queue. If we go through the entire loop and we have not successfully found any index with value 0, return false. There we go. Now this algorithm runs in both time complexity and space complexity of O(n). If you like this video, check out the other Leetcode videos I have on my channel for more practice. See you next time!